Hello. What we're going to do here is model up the thick-walled pressure vessel. So we're going to draw it, extrude the drawing to get a three-dimensional model, and then use the simulation tools to put the pressures in and see how we do. Now before we draw it out, let's just make sure down at the bottom right here we are in millimeters, because our pressure vessel is measured in millimeters. It's far easier. Okay. What we're going to do is start a sketch. Now to start a sketch, if I just click sketch, it asks me to select a plane. We're going to select the right plane. So I'll click the right plane. Okay. Now on this, what we're going to do is we're going to draw out, so I'm just centering that circle slightly, we're going to draw out a quarter of the wall of our pressure vessel. Okay, to do that I'm going to use the center point arc tool. That uses 3 clicks. So we set the center of a circle and then the 2 points along the circumference of the circle to denote an arc. We're going to do a 90-degree arc. So I'm going to set my point, center point, set my center at the origin, come out horizontally, certain distance about there, drive it up to 90 degrees, and click again. And you know, I didn't need to have my pointer exactly where the edge of the arc was going to be. I was just taking the line up vertically. Okay, you see there that sets a tangent point as well. We need a second center point arc because our thick-walled cylinder has 2 walls. So I'm going to come in again, horizontal, up to 90 degrees, and that's everything for the center point arc. So I can deselect the center point arc tool. Now before I do anything else, I'm going to dimension this. So I'm going to go to Smart Dimension, click on the arc, pull out to the left or the right, it doesn't matter. Okay, and I need to make that radius 18.5. That's the inner radius of our thick-walled pressure vessel. And then I do exactly the same with my Smart Dimension on the bigger arc, and that radius is 75. If you get that situation, don't worry, you can always come here and just click that button there which says zoom to fit. Okay, you can also manually zoom with your mouse wheel, assuming you have a mouse. Wheel towards you takes it in, wheel away from you zooms it out. Right, so we're at that point. Just to complete this sketch, we're now going to use the line tool, and we're just going to join these 2 edges together. Okay, so that creates the basic form of our pressure vessel. Okay, now if we look, it might appear, it's not too bad when we zoom out, that the vertical line looks slightly longer than the horizontal line. So it might look at, it isn't, but if we just go to Smart Dimension, sorry, I was still on the line properties, Smart Dimension, that line is 56.5, and that line is 56.5. Okay, so both lines are the same length. It's just an optical illusion. Right, so once we've got the sketch going, we're going to exit the sketch and we're going to go to the Features tab. So what we're going to do now is make this cylinder as long as we need it. So we're going to go to Extruded Boss Base tab. It automatically selects what we're going to extrude, which is the face we've drawn. There are no other faces to extrude, so it's quite happy doing that. Our cylinder was 203 millimeters long, so we go into there where it says D1 and type 203 millimeters. And again, it's rocketed somewhere off the screen. Click the tick, and again zoom us to fit us on screen. Now if you want to rotate it, you can do it using your arrow keys, though I find that slightly clunky, but I want to see that view there, because we need to get access to the two rectangular faces for the next part of this drawing. Okay. Now, if you're particularly concerned, I would at this point save this part before we go any further, because then at least we've got the basic drawing done. I'm going to save it as what shall I say? Thick wall part. Okay, so that's now saving, and just in case anything we do next is goes wrong. Now, our cylinder is made of aluminium. The material is important for what we want to do. So what we're going to do is now set that material. We're going to go to Material, right click, Edit Material. Okay. It defaults to steels, but we want aluminiums. And the aluminium we're after, if we look here, you can go through all of the alloys, and down here they say what the elastic modulus is and what the Poisson's ratio is. So aluminium is 0.33 pretty much constantly. But if we go down through these alloys, you'll see they all have ever so slightly different values of Young's modulus. We're looking for one that has a Young's modulus of 73 gigapascals and a Poisson's ratio of 0.33. And I know just from experience that 2014 alloy in the list has got exactly the data we need. So we're going to set 2014 alloy, click apply, and then click close. You see here now, it's changed the material to be aluminium. Right, so what we need to do now is we need to create a reference line on one of these faces for when we do our FEA check. Okay, to do that we need to set some reference points up. So the first thing we're going to do is, we're still in the Features tab, we're going to create reference geometry, and we're going to create a reference axis. Okay, so click axis. Okay, and it basically wants us to select 2 points with which to set our reference axis against. Okay, we're going to select the two rectangular faces of our drawing, and you'll see in yellow here the reference axis has appeared running bang down the center of our pressure vessel. That's exactly what we want, so we click OK, and that reference axis now appears on our drawing. Okay. What we then need is a plane to draw the split line on. Okay, so to get that we go back to reference geometry. This time we're going to put a reference plane in. Okay, and that reference plane is going to be set with reference to axis 1 and that plane there. We can also pick that face there, but it doesn't like, it's in the wrong direction if we select that face, so I'll deselect that. I tend to always select the closest one, and you can see it's created a new drawing plane at 90 degrees to that face. We want it running straight down the very middle of this wall, so we come in to the angle here and change that to be 45 degrees, and then our reference plane has appeared there, fully defined. Click the tick and everybody's happy. Okay, the final part of this drawing is to put in the split line, and I'm going to put it in going to move my part around, okay, and rotate it just slightly. There we go, just bear with me 1 second. There we go. So I tend to like to use this. It's always important we remember which face we've put our split line on. So I tend to always try and keep it to the left-hand face, then I know what I'm doing. So the final thing we do is going to put a split line onto this face of the cylinder. Okay. Now, if you look for a split line, it's actually hidden away slightly in some of the menus. So we need to go to Insert, Curve, Split Line. Okay. Click that. And it's now asking us for a type of split, which we're going to set as intersection. And that intersection split, it defaults to plane 1, but we don't want that to be plane 1. We want the first selection to be face 1, and we want the second selection to be plane 1. Or was I right the first time? Take that out. Face. No, I was right first time, sorry. So we want the first one to be plane 1 and the second option to be face 1. That bit always catches me out. So it's slightly confusing. So you're doing the split line along the plane but splitting face 1 with that split line. Click OK. And now what you'll see is the lines appeared on the drawing there, and you can select it as an entity. If I just flip a drawing around, you'll see the split, the plane appears there, but the split line doesn't appear on that face. Okay, which is what we are looking for. Okay, let's go to that one, and then I should be able to take it back to that one. So that's our drawing done. So we finished all the drawing, at which point, again, I save it. Okay. So the second part is now to do the simulation. So what we do is we need to constrain a few of these parts. So what we need to basically say is this face can't move. Okay, this face can't move. And so what we're going to do is go into the simulation tab, and we're going to create a new study. Okay, that's not what I wanted to do. Simulation tab, new study. That's what we were after. Okay, and we're going to do a new static study. Click the tick. Okay, so for what we're doing, we need to, the model needs to be fixed in 3 dimensions. Okay, so we need to lock 3 faces of this model. We do that by adding fixtures. So we're going to come here, click the drop down menu, and we want some roller slider fixes. Okay, and the roller slider restraints need to go on the 2 rectangular faces like that, and onto the opposite face to the split line. So we should have 3 roller slider fixtures. Click OK. And again, now that's all in place, I'm going to bring my geometry back to look at a view I prefer, which is not that one. It was supposed to be that one. Oh, I will get there. We'll find it in a moment. That one will do, because I need to get access to these 2 faces here and that split line there. So that's good. So now we've put these fixtures on, okay, and you'll see everything we put in appears here. Okay, we need to put an external load on. Well, our external load isn't actually external, it's internal, but we're going to put, so we come to external loads and we're going to come and put pressure, and the pressure is going to be applied to that internal face, normal to the selected face. So we've set the pressure inside. Now this pressure is in newtons per meter squared. We have 6.5 meganewtons per meter squared of pressure. So 6.5 E6, 6.5 meganewtons. Press enter on that, it converts that pressure for you. So we know we've got that right. Okay, so that's the gauge pressure. So on the external surface of this pressure vessel, we also have a pressure. So we need to put a second external load on, okay, which is on that face. And that load is 1 bar atmospheric pressure, 100 kilonewtons per meter squared. Okay. That's all our pressures added. Okay, and again, I'm always of a mind at this point to save what I'm doing. Excuse me. So now all that's left is to run our simulation. But what I tend to do first is just check. So what the FEA analysis is going to do is split our model into lots and lots and lots and lots of tiny pieces and stick them together to create what we call a mesh over the model. Now if we create the mesh, we can see that it does take a few seconds for this to come in. Okay, that, where's my mesh tool? It's appeared here now. We can go from a very coarse mesh to a very fine mesh. Okay, I'm going to keep it somewhere in the middle just for the purposes of this demonstration. The finer the mesh, the longer it takes to simulate, the more resources it will take to simulate, but the better spread of data you'll get. A very coarse mesh, you'll get a wider spread of values. Okay, so if we set that mesh up, you can see there it did it fairly quickly. Okay, it's checking for distortions, and there's my relatively middle of the road mesh for our FEA analysis. Okay, so we're now going to run our simulation. Okay, so we run this study, and you tend to have to look down in this part quite a lot, just to make sure that things are working. And then this window appears here. This could take a couple of minutes to happen. Okay, which if it does, we can have a look at the assignment that you are being asked to do. He says, just bear with me a second. So that's chuntering through. It's having to think about it. The thick-walled pressure vessel user guide goes through quite a lot of what we're looking at here. Okay. Funnily enough, when it gets to 18.2, it doesn't normally take much longer after this. But we'll look. So it looks like it might be about to give us some results. So just while I'll keep an eye on that while I show you this. Okay. Yep, so the results have come through. That is showing us the spread of pressures, okay, within the thick-walled cylinder. So you can see how the greatest pressure is on the inside, and the amount of pressure gets lesser, lesser, till we get to the outside. Now this defaults to a von Mises stress. We don't want that, so we need to right-click there, click Edit Definitions, okay, and change the von Mises to SX normal stress. Okay, click the tick, okay, and then it changes the view somewhat. And I'm never quite sure if those arrows move themselves. Okay. But what we can also do with the results options, okay, is edit whether we see stresses or strains. Okay, we also see displacement. Okay, and what that split line is there for, okay, is that we can then ask this thing to have a look at the stress, okay, on selected entities and select our split line. Okay, if we click update on that, then what we get here is, in this bottom part here, a table of all of the stresses running along that line. Okay, starting compressive and bringing it through. Okay, and you can see how, just to show you, it also shows you the XYZ coordinates, so you can see that it's always on the 0 point. Okay, the Y-axis is that way, and the Z-axis is that way. Okay, based on this drawing. Okay, so the X-axis never changes because we're going along that plane, If I draw it to look directly at the x-axis, we're looking straight at the face. If we look directly at the y-axis, we're looking at that face, and if we look directly at the z-axis, we're looking at that face. So you can see which direction our dimensions are changing in. So our x never changes, y changes, and z changes. Y is positive and z is negative, but they're the same magnitudes because we're going diagonally. Okay, so those results should tally fair, and these results are easy to copy all of those values, copy them, and you can paste them into an Excel file for analysis. Okay, I'll just deselect them because it's hiding the drawing. Just come back again and we'll view the cylinder from one of the angles again. Okay, but that is how you perform the FEA analysis on the thick-walled cylinder. I hope it's been useful.